Welcome to the introduction to section 2.5. This is a big idea here called the chain rule. We're thinking about how to take the derivative of functions that are a composition of two functions. So we have a function here, f of x. It's the square root of x squared plus 2. We don't know how to take the derivative of this function yet. The product rule, the quotient rule, the power rule won't quite get the job done for us. And it's because this function f, capital F, is a composition of functions. It's f composed with g. Hopefully this looks familiar. If not, go back to chapter 1. And there's some work on composition of functions in the beginning there. What are those functions f and g that make this up? So the outside function f is the thing that says take the square root of. So that would be the function square root of x. The inside function g is the thing that's going into that square root of function, that square root function, which is x squared plus 2. So g of x is the function x squared plus 2. If we compose these, as is written here, f of g says everywhere you see an x in square root of x, replace it with g, which is x squared plus 2, and that would give us the function capital F, which is square root of x squared plus 2. So if composition, again, isn't something you haven't thought about in a while, go back to chapter 1 or maybe check out some Khan Academy videos. Okay, those two functions we do know how to take the derivatives of. In fact, f prime of x, that's x to the 1/2, so the derivative is 1/2 x to the negative 1/2, or 1 divided by 2 square root of x. And g prime of x is just 2x. Okay, so let's keep these four functions in mind: f, g, f prime, and g prime. And our job is to try to write the derivative of capital F in terms of those four functions. All right, so I started this job for you because capital F being a composition function, it's a bit of an algebraic battle here to get through the derivative. So we use the limit definition of the derivative. The first step, it's the limit as h approaches 0 of the square root of x plus h quantity squared plus 2 minus the square root of x squared plus 2, all divided by h. Multiply here by 1 in this nifty fashion where I just changed the sign in the numerator to positive. And then I've done the job of doing that algebra for you. And after 3 steps of algebra, we get down here to the limit as h approaches 0 of 2x plus h over the square root of x plus h squared plus 2 plus the square root of x squared plus 2. Okay, so now we're at a point where we can take the limit in the numerator as h goes to 0. This term goes to 0, and we're left with 2x. In the denominator, as h goes to 0, just this term down here goes to 0, and we're left with the square root of x squared plus 2, that's from the first term, plus another copy of the square root of x squared plus 2. Okay, so that tells us that the function, the derivative we were looking at, f prime of x, is 2x, and in the denominator we have 2 copies of the square root of x squared plus 2. Okay, you're going to say, Todd, go ahead and cancel those 2's. Let's simplify this derivative. Of course, we could do that, but for the sake of illustrating what I want to illustrate, I am not going to do that. I'm going to rewrite this in this way. This is the same as 1 divided by 2 times the square root of x squared plus 2 times 2x. Okay. I did that for a reason. I want to go back up here and let's just focus on the function g of x and its derivative. G of x is x squared plus 2. Its derivative is 2x. I see that both of those things showing up down here. Let's pick a different color. Here inside of this square root is g of x. And here is g prime of x. Okay, let's see. How can we handle the rest of this quotient here? 1 over 2 square root of something. Well, 1 over 2 square root of something, if we go back up above here, is exactly f prime. And what's going into f prime? Everywhere there was an x in f prime, it's being replaced with g of x. So this can be rewritten then as f prime of g of x times g prime of x. Okay, there's an example. We rewrote, let's go back and make sure we see what we did. We rewrote capital F as a composition of two functions, f composed with g. We looked at their derivatives, which we could take. The only tool we had at this point for taking the derivative of capital F was the limit definition. We did that, and then we were able to rewrite the derivative of capital F in terms of the derivative of the two functions it was composed of, the derivatives of the two functions it was composed of. So this is the chain rule. If f and g are both differentiable functions, and capital F is the composition of those two functions, then it is also differentiable, and the derivative of f is f prime of g times g prime of f. So g prime of x, sorry. So I like to think of this as the derivative of the outer function evaluated at the inner function times the derivative of the outer function. Okay, let's see if we can put this into practice. This first example, let's see, we have x squared minus 3 to the 16th. So the thing playing the role of the outer function is the 2 to the 16th power. We could take the derivative of x to the 16th just using the power rule, and that's exactly what we're going to do here. So this thing looks like the composition of two functions, for the functions being, let's call this capital F for a minute. Sorry about that. Let's rename that thing. So this looks like f of x is x to the 16th, and going into f of x is x squared minus 3. Okay, well, f prime is just 16x to the 15th, and g prime is just 2x. And so the derivative of capital F, according to the chain rule, is the derivative of lowercase f evaluated at g times the derivative of g. Okay, so the derivative of lowercase f is 16x to the 15th, but everywhere I see an x there, I need to replace it with g of x, which is x squared minus 3. 16 times x squared minus 3 to the 15th times g prime, which was 2x. Okay, if we go back to the beginning here, we see that the 16 came down, we went to 1 less power. Sorry, let me change the color. The 16 came down, we went to 1 less power. We left the inside function alone, which was x squared minus 3, and then we multiplied here by the derivative of that inside function, which is x squared minus 3. If you want to write out the composition every time and follow the pattern of the chain rule, you can, but for sake of efficiency, we want to be able to recognize these things a little bit quicker. So let's see if we can do that in the next two examples. Okay. Let's see here. I'm going to rewrite g of x ever so slightly. Sine cubed is the same thing as sine of x cubed. So now when we take the derivative, the same thing happens that happened above. The derivative of g. We take the derivative of the outer function. That happens with the product rule. The 3 comes down. We don't change the inner function. We go to 1 less power. And then our job, though, is still to multiply by the derivative of sine of x. Okay, 3 came down, we went to 1 less power, that's the product rule. We left the inside function alone, and then our job is to multiply by its derivative. The derivative of sine is cosine, and so that tells us that g prime of x is 3 sine of x squared times cosine of x. That can also be notated 3 sine squared x cosine x. Okay, let's see. Slightly different game here for h of x. I'm going to rewrite h again before I try to apply the chain rule. So h is sine of x squared, and that whole thing is being cubed, is technically another name for this function. Okay, here we go. So again, the 3 can come down, we can go to 1 less power, we leave the inner function alone. So h prime, the 3 comes down, we have sine of x squared, we go to 1 less power. So we just did the the power rule, pretending that thing in parentheses was just x. But now because it's not just x, we need to multiply by its derivative. So we need to multiply by the derivative of sine of x squared. However, the derivative of sine of x squared also requires the chain rule. So here we need the chain rule inside of the chain rule. So let's do it. Okay, let's write down everything we've had so far. 3 sine of x squared all being squared. Now, again, the inner function is x squared. So we take the derivative of the outer function. The derivative of sine is cosine. And we leave the inner function alone. Just like we did up here. The outer function was cubed. We took its derivative, left the inner function alone. Here, the outer function is being played by sine. Its derivative is cosine. The inner function is x squared. It gets left alone. But we do need to multiply by its derivative. And that is a derivative we can take without needing the chain rule. So we have 3 sine of x squared times cosine of x squared times the derivative of x squared, which is 2x. So there was a chain rule inside of a chain rule. We can rewrite this thing. We don't have to. The 3 and the 2x are 6x. This term is sine squared of x squared and cosine of x squared. Okay, there's the chain rule and 4 examples, I guess, technically, because of the one that was used to motivate it. So again, the key is take the derivative of the outside function as we did in all of these, leave the inside function alone, but because that inside function isn't just x, we need to multiply by its derivative, is what the chain rule says. So derivative of the outer, leave the inner alone. So evaluate it at the inner function, then multiply by that derivative. Okay, take a stab at the section 2.5 activity.